Okay, so do you see the screen?
Yes.
Yes.
Okay, let's begin then. So our main goal for today is to construct the so-called polar decomposition of linear operators on a Hilbert space. And before we can do it, we will need to discuss some classes of linear operators between Hilbert spaces. Specifically, we are going to discuss some geometric properties of linear operators, and then to characterize such geometric properties in algebraic terms. So let's start with isometries. Just in case, let's recall the definition. If x and y are normed spaces, then linear operator t from x to y is an isometry if it preserves the norm. That is, the following inequality holds. So now we have the following characterization of isometries between Hilbert spaces. So proposition. Suppose we have two Hilbert spaces, H1 and H2. And suppose that U is a bounded linear operator from x1 to x2, h1 to h2. Then the following conditions are equivalent. Condition 1, U is an isometry. Condition 2, U preserves the inner product. So the following identity holds. And property 3 is the following simple algebraic formula. U star U is the identity map on H1. Okay, now let's start to prove this. Let's start with condition 3. So this equality holds. Well, in general, if you have two operators, let's recall that two operators between Hilbert spaces are the same, if and only if the associated ciscollinear forms are the same. So this is equivalent to the following identity. This is the ciscollinear form associated with the first operator, and this is the form associated with the identity operator. This is just the inner product. And let's now observe that the left-hand side of this formula is nothing but the inner product of ux and uy. And we see now that conditions 2 and 3 in our proposition are equivalent. Okay, let's now continue this. We now recall that two ciscollinear forms are the same, if and only if their restrictions to the diagonal are the same. This is a corollary of the polarization formula, which was discussed at the previous lecture. So we see that this equality is equivalent to the same equality in the case where y and x are the same. And this is precisely condition 1, because if we substitute y equals x here, we see that the norm of ux squared equals the norm of x squared. So by taking the square roots, we get the following formula. And this means precisely that U is an isometry. Okay, this completes the proof. Let's now look at co-isometries. So the definition is as follows. If we have two normed spaces, x and y, then a linear operator t from x to y is called a co-isometry. Co-isometry if it takes the open unit ball of x onto the open unit ball of y. So these two sets denote the open unit balls. And let's recall the following useful fact, which establishes a duality between isometries and co-isometries. If x and y are Banach spaces, and T is a bounded linear operator from x to y, then T is an isometry. Well, so this is fact 1. T is an isometry if and only if the dual operator T star is a co-isometry. And dually, T is a co-isometry if and only if the dual map is an isometry. Now combining this with, so this fact was proved in the previous turn, so I'll not repeat the proof now. Actually, we will in the case of Hilbert spaces, it's easy to see that conditions 1 and 2 are equivalent, just because Hilbert spaces are separable and T double star equals T. And the proof of the second fact is essentially more difficult than the proof of the first fact. So even if you don't know this fact, the first part of this fact is a rather simple exercise. And this is exactly what we will use. So now if we combine this with the previous characterization of isometries, we get the following corollary. Corollary 1. If we have two Hilbert spaces H1 and H2, then a bounded operator U from H1 to H2 is a co-isometry if and only if U star is the identity map of H2. This is just the dualization of the previous characterization of isometries. And as a special case, we obtain an algebraic characterization of unitary operators. Well, first of all, let's recall the standard definition of a unitary operator. If H1 and H2 are Hilbert spaces, then a bounded operator U from H1 to H2 is called a unitary operator if it is bijective and preserves the inner product. U is bijective and U preserves the inner product. So now we have the following corollary 2. A bounded operator U from H1 to H2 is unitary if and only if U is a bijective isometry. And if and only if U is inversible. And the following formula holds: U star equals U inverse. Well, again, this is a special case of our previous characterization of isometries. So U is in isometry if and only if U star U is the identity map. But if you already know that U is bijective, this quality is equivalent to this one. U star equals U inverse. Okay. By the way, this characterization of unitary operators is consistent with our earlier definition of unitary elements in a C-star algebra. So we defined unitary element of a C-star algebra as an element satisfying this last equality: U star equals U inverse. So for operators, this algebraic definition of unitary operators is equivalent to the geometric definition given above. Okay, now let's look at another class of operators, namely at orthogonal projections. So we have the following definition. If H is a Hilbert space, then a bounded operator P on H is an orthogonal projection if there exists a closed vector subspace H0 in H such that P restricted to H0 is the identity map and P restricted to the orthogonal complement is 0. So equivalently, this means that P is a projection, which means that P squared equals P. P is idempotent. And the kernel and the image of P are orthogonal to each other. This follows from the fact that H0, so H is decomposed in the direct sum of H0 and the orthogonal complement. So these two definitions of an orthogonal projections are equivalent. By the way, the Russian for orthogonal projection is orthogonальный проектор. Orthogonальный проектор. Очень многие любят говорить проекция, но на самом деле традиционная терминология именно такая, проектор. Okay, and here is an algebraic characterization of orthogonal projections. So we have the following result position. a bounded operator P on a Hilbert space H is an orthogonal projection if and only if P is self-adjoint and idempotent. To prove this result, we first observe that P is a projection, if and only if P star is a projection. That is, P is idempotent if and only if P star is idempotent. This is clear. So we have to show now that a projection is orthogonal if and only if it is self-adjoint. So suppose now that P is a projection. So when is it idempotent? Well, we already know that both P and P star are projections. And two projections are the same, if and only if their kernels are the same, and their images are the same. So this is a simple observation which holds for any pair of projections. Two projections are the same if and only if they have the same kernel and the same image. Okay, and now let's write this in the following way. Let's recall that for each operator P, the kernel of P star is the orthogonal complement of the image. So the first equality can be written in this way. And also for each operator, the image of the closure of the image of P star is the orthogonal complement of the kernel of P. But here the image is automatically closed because it is projection, a continuous projection. And so the second equality has the following form now. The image of P is the orthogonal complement of the kernel of P. And it's clear now that both equalities are equivalent to each other, and they mean precisely that the kernel and the image of P are orthogonal. That is, P is an orthogonal projection in the sense of our definition. And this completes the proof. Okay, and now we are going to introduce a class of operators which contains all isometries, all co-isometries, and all orthogonal projections as special cases. So we'll have the following theorem. Suppose that H1 and H2 are Hilbert spaces, and U is a bounded operator from H1 to H2. Then the following conditions are equivalent. Condition 1, U satisfies the following identity. So by the previous proposition, this means that U star U is a projection, an orthogonal projection. It is obviously self-adjoint, and this quality means that this operator is a projection. Condition 2, U equals U star U. Now condition 3, U star is an orthogonal projection. U star is an orthogonal projection. Condition 4, U star equals U star U star. And finally, condition 5, which is more geometric than the previous 4 conditions. The restriction of U to the orthogonal complement of its kernel is an isometry from the orthogonal complement of the kernel to H2. And moreover, if these conditions are satisfied, so in this case, U star U is the orthogonal projection onto the orthogonal complement of the kernel of U. And U star is the orthogonal projection onto the image of U. Okay, and before we prove this theorem, let's introduce the terminology. So by definition, an operator U satisfying the above conditions is called a partial isometry. In Russian, частичная изометрия. And the projections which are mentioned in the statement of the theorem also have special names. The projection U star U is called the initial projection. Of U. And the second projection U star, which projects onto the image of U, is called the final projection. In Russian, initial projection is начальный проектор. And final projection is финальный проектор. Или конечный проектор, кстати, даже чаще говорят, наверное. Финальный или конечный проектор. Well, also before we prove this theorem, let's make some simple observations which are immediate from the statement. First, let's observe that U is a partial isometry if and only if U star is a partial isometry. This follows from the statement because if you look, for example, at conditions 1 and 3, it's clear that to get 1 from 3, we simply replace U by U star and U star by U. So this implies that U is a partial isometry if and only if U star has the same property. The second observation is that each isometry is a partial isometry each coisometry is a partial isometry, and each orthogonal projection is also a partial isometry. And again, to see this, it suffices to look, for example, at condition 1. So condition 1 implies that if U is an isometry, then U star U is the identity map, so condition 1 is satisfied. And if U is a coisometry, for the same reason, condition 3 is satisfied. And finally, if U is an orthogonal projection, then U star equals U squared, and so condition 1, and all these conditions are also satisfied. And observation 3 is essentially a picture which illustrates the behavior, the geometric behavior of a partial isometry. So let me draw a picture. Well, this is H1, first space, and this is H2. So H1 is decomposed in the orthogonal direct sum of the kernel of U and the orthogonal complement of the kernel. So if U is a partial isometry, then by condition 5 of our theorem, the restriction of U to the orthogonal complement of the kernel is an isometry. So U takes the orthogonal complement of the kernel isometrically onto its image. And this is an isometry. And of course, the kernel of U goes to 0. Well, let's now recall that the kernel of U, well, this is not the end of the story, because we can now look at U star. So the kernel of U, the orthogonal complement of the kernel of U equals the image of U star. Well, why is it so? In fact, for each bounded operator, the kernel of U is the orthogonal complement of the kernel equals the closure of the image of U star. But in our case, the image is closed. It's immediate from the definition of a partial isometry. So the image is closed and we have this equality. And for the same reason, the image of U equals the orthogonal complement of the kernel of U star. And we also know that U star is a partial isometry. So for the same reason, U star restricted to this subspace here is an isometry onto this subspace. This is U star, and it is also an isometry. And finally, if we compose these two maps restricted to the respective subspaces, then we get the identity maps. The identity map here and the identity map here. And this is immediate from conditions 1 and 3. So both the operators are identical. Since they are projections, they are identical on their images. That is, on these two spaces. And of course, the kernel of U star goes to 0. So this picture is an illustration of the geometric meaning of a partial isometry. So when we restrict U and U star to the respective subspaces, they become unitary isomorphisms between these subspaces, and they are inverse to each other. Okay, let's now prove our theorem. Well, it's not very convenient because I cannot keep the statement on the same part of the whiteboard. So first, let's prove that conditions 1 and 2 are equivalent. And it's very easy to show that 2 implies 1. So to show that 2 implies 1, we simply multiply 2 by U star on the left. To get 1 from 2, we simply multiply 2 by U star on the left. And that's it. Now to show that 1 implies 2, so we assume that U star U is a projection, and we want to show that U equals U star U. So we'll take the difference of these two operators, take the square of the norm, and apply the C star identity. So this is U multiplied by 1 minus U star U. And by the C star identity, this equals the following. So we must take first the adjoint of this operator, which is 1 minus U star U multiplied by U star. So this is the adjoint operator. And then take the initial operator, U, multiplied by 1 minus U star U. Okay, and now since U star U is a projection, it's immediate that, for example, this product is already 0. So if P is a projection, then 1 minus P multiplied by P is 0. So this is 0. And we see that 1 implies 2. Okay, let's now look again at the statement. Let's now observe that 2 is equivalent to 4. To see that 2 is equivalent to 4, we simply take the adjoint operators. We apply the involution, and we see that 2 is equivalent to 4. And also, it's clear that 3 is equivalent to 4, because we already know that 1 is equivalent to 2. So if we replace U by U star and U star by U in 1 and 2, we get 3 and 4 respectively. So to see that 2 is equivalent to 4, we simply apply the involution. And 3 is equivalent to 4 because 1 is equivalent to 2. And finally, let's look at the last condition, condition 5. So we will show that this geometric condition is equivalent to condition 4. We'll show that phi is equivalent to 4. Well, let H0 denote the orthogonal complement of the kernel of U. And let's recall that for each bounded linear operator T, the orthogonal complement of the kernel of T equals the closure of the image of T star. So when we apply this to our operator U, we see that U star, the joint operator, takes H2 to H0. So the image of U star is contained in the orthogonal complement of the kernel. And this inclusion implies the following identity. If we restrict U to H0 and consider it as a map from H0 to H2, then the joint of this operator is just U star. So this follows from the previous inclusion. So in the general case, these two joints could be different if U star doesn't take H2 to H0. But since U star takes H2 to H0, these two operators are the same. Hence, let's now look at condition 5, which states that the restriction of U to H0 is an isometry. So now 5 can be written in the following way. The restriction of U star U to H0 is the identity map of H0. This is immediate from the previous line and from our characterization of isometries. But we already know that H0 is, so again we look at this formula. H0 is the closure of the image of U star. H0 is the closure of the image of U star. So these operators are the same if and only if the restrictions to the image of U star are the same, because the image of U star is dense in H0. Or equivalently, this means that the compositions of these operators with U star are the same, and we get this identity. But this is precisely condition 4 of our theorem. And this completes the proof. Okay, and as a special case of this theorem, we get the following algebraic characterization of co-isometries. Corollary. A bounded linear operator U from H1 to H2 is a co-isometry if and only if the restriction of U to the orthogonal complement of the kernel is a unitary operator between this orthogonal complement and H2. Oops, just a moment. So if U is a co-isometry, if and only if this map is unitary. This operator is unitary. Well, why is it so? If we look again at the statement of the theorem, So we know that U is a co-isometry if and only if U star, so we look at condition 3, U is a co-isometry if and only if U star is the identity map. So this implies that U is a co-isometry if and only if U is a partial isometry whose final projection is the identity map. Or equivalently, this is a surjective co-isometry. But by condition 5, U is a surjective co-isometry if and only if U is a unitary operator between the orthogonal complement of the kernel and H2. Okay, we are now ready to discuss the polar decomposition of linear operators between Hilbert spaces. Polar, oops. Okay, let's start with some motivation. Well, as you probably know, each complex number Z can be uniquely represented in the following way. A plus IB, where A and B are real numbers. Oh, okay, so this is just secondary school. And we already know that this formula has an operator analog. So we know that each linear operator T on the Hilbert space can be uniquely decomposed in the following way: T1 plus I T2, where T1 and T2 are self-adjoint. So this is the operator analog of the previous formula. Okay, let's now recall that there is another useful formula for complex numbers, namely each complex number Z can be decomposed in the following way: the modulus of Z multiplied by the following exponent. Or we can write it in the opposite order, because the multiplication in the field of complex numbers is commutative. So now our natural question is there an operator analog of this formula? And it turns out that the answer is yes. So our goal will be to show that the answer is yes. And more precisely, we will get two formulas, two polar decompositions of a linear operator. And there will be two formulas because the multiplication of operator is not commutative. Okay, now to obtain such formulas, we have to answer two natural questions. Namely, what is the operator analog of the modulus of the complex number? And what is the operator analog of the second factor here, e to the power I phi? As for the modulus of an operator, well, we essentially already know the answer. So we have the following definition. If T is a bounded linear operator between two Hilbert spaces at H1 and H2, then we define the modulus of T to be the square root of T star T. So T star T is a positive operator on H1, so we can take the square root, and the result will be a positive operator on H1. Actually, at the previous lecture, we defined the modulus of any element in any C star algebra. So this is just an operator analog. And let's also recall that this definition is consistent with the functional calculus. Namely, if T is a self-adjoint operator on a Hilbert space, then this operator, the modulus of T, is nothing but the function modulus applied to our operator. Okay, now let's try to answer the question, what is the natural operator analog of this exponent, e to the power I phi? Well, this complex number sits on the unit circle, centered at 0 of radius 1. And the unit circle consists precisely of the unitary elements of the complex plane. So the complex plane is a C star algebra, and the set of unitary elements in C in the complex plane is just the unit circle. So a reasonable conjecture is that a correct operator analog of this exponent is a unitary operator. But it turns out that this conjecture is too naive. And here's a useful exercise, which, as far as I remember, was in one of the previous exercise sheets. An exercise. There exists a bounded operator T on a Hilbert space, actually on any infinite dimensional Hilbert space, such that T cannot be decomposed as the product of the unitary operator and the positive operator, where U is unitary and S is positive. By the way, such a decomposition is always possible in the finite dimensional case. This is more or less classical theorem from linear algebra. So the point is that in the infinite dimensional case, we don't have such a decomposition in general. And the way out of this situation is to replace unitary operators by partial isometries. So we have the following theorem. Theorem about polar decompositions. If H1 and H2 are Hilbert spaces, then for each bounded linear operator T from H1 to H2, there exists a partial isometry. U, also between H1 and H2, such that the following two formulas hold. So here is the first formula, and this is the first polar decomposition, or sometimes some people call it the left polar decomposition. And here the second formula, modulus of T star multiplied by U. So these are the polar decompositions of our operator. But this is not the end of the story. We can also choose U in such a way that the following two properties are satisfied. The kernel of U is the orthogonal complement of the image of the modulus of T. And this is the same as the kernel of T. And also we can choose U in such a way that the image of U is the orthogonal complement of the kernel of the modulus of T star. And this is the same as the closure of the image of T. Okay, so this is the polar decomposition theorem. Well, the first two formulas, I mean, the polar decompositions themselves are more or less self-explanatory, so maybe I'll not comment about these formulas. They're quite natural, taking into account the above motivation. So maybe I'll make some comments about the last two formulas in the last line of the statement. Roughly, these formulas mean that such an operator U is the most economical way to write such a polar decomposition. Look, for example, at the second formula. If U satisfies the polar decomposition formula, then it's clear that the image of T is contained in the image of U. And since the image of Q is closed, we see that the closure of the image of T is necessarily contained in the image of U. So the second formula here means that, this formula means that the image of U is as small as possible. And also the first formula here has also a rough geometric meaning, namely, if U satisfies the polar decomposition formula, then we already know how U behaves on the image of the modulus of T. So it takes the modulus of Tx to T of x. And this formula means that if you take something which is orthogonal to the image of this operator, then U takes this vector to 0. So again, this can be interpreted as the property that U is the smallest possible operator, the smallest possible partial isometry, satisfying the polar decomposition formula. Okay, to prove this theorem, we need a couple of lemmas. So lemma 1. Lemma 1. So suppose that H1 and H2 are two Hilbert spaces, and T is a bounded operator from H1 to H2. So for each operator T, the following conditions are satisfied. Condition 1, the kernel of T equals the kernel of T star T and equals the kernel of the modulus of T. And condition 2, the closure of the image of T equals the closure of the image of T star and equals the closure of the image of the modulus of T star. Well, to prove part 1, we first observe that it's clear that the kernel of T is contained in the kernel of t star t. So obviously, if t annihilates a vector, then t star t also annihilates this same vector. Now, to get the opposite conclusion, we observe that for each element x in H1, the norm of tx squared is, well, by definition, this is the inner product of tx by itself. And this is the inner product of t star tx and x. And this equality implies that if t star t annihilates some vector, if t star t of x is 0, then t of x is also 0. So this implies that the kernel of t equals the kernel of t star t. So this proves the first equality. And to get the second equality, we simply apply this to the modulus of t. So if we apply the same this formula to the modulus of t, we conclude that the kernel of the modulus of t equals the kernel of the modulus of t squared. Well, the modulus of t is self-adjoint, so we get this equality. But the modulus of t squared is nothing but t star t, just by the definition of the modulus. And that's it. So this completes the proof of part 1. And to prove part 2, we do the following. We apply part 1 to the adjoint operator, t star, and take the orthogonal complements. And what we get is exactly formula 2. Simply because the orthogonal complement of the kernel of t star is the closure of the image of t.
Решили построить самолет. Только не хватит.
Идите пока, еще не закончил. Идите, давайте. I'm sorry, just a moment. Давайте быстро, чтобы не мешали. Все, бегом. Sorry, that was a technical break. Good, so this completes the proof of lemma 1. And one more lemma, lemma 2. Lemma 2. If t is a positive operator on a Hilbert space H, positive operator on H, and S is an arbitrary bounded operator from another Hilbert space H prime to H, then the product S star TS, which is an operator on H prime, is also positive. The proof is very easy. Let's recall that an operator on a Hilbert space is positive if and only if the associated quadratic form is non-negative. So we simply look at the quadratic form of the operator S star TS. So this is such an inner product. Then use the definition of the adjoint operator and write this in the following form. And we see that this is the quadratic form of the operator T evaluated at Sx. So it is positive, it is non-negative because T is positive. And that's it. So this implies that the quadratic form of S star Ts is also non-negative. And this completes the proof of lemma 2. Okay, let's now prove the polar decomposition theorem. So we want to construct a partial isometry U, which satisfies such that the product of U and the modulus of T is T. So we want to construct U in such a way that U takes each vector of the following form, the modulus of T applied to X, to T of X for each X in H1. To show that such an operator exists, let's do a little calculation. So let's calculate the norm of the modulus of Tx squared. So this is the inner product of this vector by itself. So since the modulus of T is self-adjoint, we can write this in the following way. And the modulus of T squared is T star T. So again, this is the inner product of Tx by itself. That is the norm of T of X squared. So this chain of equalities implies that there exists a well-defined isometry let's denote it by U0 from the image of the modulus of T to H2, which takes each vector of the form modulus Tx to Tx. It is well defined because of the previous line. So if the modulus of Tx is 0, then Tx is 0. So this is well defined, and it is an isometry again by the previous line. Also, we can extend it by continuity to the closure of this image. So I put the closure here. So obviously, each isometry defined on a vector subspace of a norm space uniquely extends to the closure of this subspace. And so now we extend it to the whole H1 in the following way. We now define U. We now define an operator U from H1 to H2 by the following rule. So U of X will be U0 of X if X sits in the closure of the image of the modulus T, and 0 if X sits in the orthogonal complement of this subspace. So then it's immediate from the definition that U is a partial isometry. Because U0 is an isometry and the kernel of U is just the orthogonal complement of the image of the modulus of T. So by construction, the kernel of U looks as follows. And this is exactly what we wanted to achieve. And also we wanted to show that the kernel of U equals the kernel of T. This was in the statement of the theorem. Well, since the modulus of T self-adjoint, we see that the image of this operator equals the orthogonal complement of the image of this operator equals the kernel of the same operator. This is because it is self-adjoint. And if we now apply lemma 1, we see that this is the kernel of T. So the kernel of U is exactly what we are looking for. So it equals the kernel of T. Also, we wanted to show that the image of U equals the closure of the image of T. Well, since oh, by the way, I forgot to say that it's immediate from the construction. Just a moment. Okay, so it's clear from the construction that U satisfies the first polar decomposition formula. Namely, T is the product of U and the modulus of T. This follows from this equality. And so this implies that the image of T is contained in the image of U. But since the image of U is closed, it is a partial isometry, we conclude that the closure of the image of T is contained in the image of U. Now, since U vanishes on the orthogonal complement of the image of the modulus of T, this equals the following. This is U applied to the closure of the image of the modulus of T. And by construction, U takes this image to the image of T. So by continuity, it takes the closure of this subspace to the closure of the image of T. And now this chain of conclusions implies that we actually have the following. The image of U is exactly the closure of the image of T. And this is exactly what we wanted to show. Also, by lemma 1, this is the same as the closure of the image of the modulus of T star. And this is the orthogonal complement of the kernel of this operator. And again, this is one of the equalities that we had to show. Okay, but this is not the end of the story, because we also want to get the second polar decomposition. So we also want to show that T equals the product of the modulus of T star and U. To prove this equality, let's start with a short observation. So we observe that well, maybe it would be better to start a new page. Let me see. Yes. Well, let's start a new page here. So let's observe the following. Well, U star U, since U is a partial isometry, U star U is an orthogonal projection. So actually, this is the orthogonal projection, the orthogonal projection onto onto its image, which is the orthogonal complement of its kernel. And by lemma 1, this is the orthogonal complement of the kernel of U. And the orthogonal complement of the kernel of U by construction is the closure of the image of the modulus of T. So this observation implies that if we combine this projection with the modulus of T, so this projection leaves the image of the modulus of T is invariant. So this equals just the modulus of T. And if we take the adjoint operators here, we get that the modulus of T equals the modulus of T multiplied by U star U. And let it be formula 1. So for future reference, let's give a number to this formula. Okay. Now to get the second polar decomposition formula, we do the following. So we already know that T is the following product. So by taking the adjoint operators, we conclude that T star equals modulus of T multiplied by U star. And if we multiply these two equalities, we get the following. Okay. And now taking the square roots, we conclude that the modulus of T star is the square root of U modulus of T squared U star. Okay, let's now simplify this a little bit. So I claim that this square root is actually the following operator. And to see this, we simply take the square of this operator. So this will be the following expression. And now by formula 1, this product here is just the modulus of T. So this is just the following operator. This follows from Formula 1. And now we can take the square roots again. Here we essentially use the lemma 2 because we already know that this operator in brackets is positive. Well, the modulus of t is positive, and this operator is also positive by lemma 2. So by taking the square roots, we conclude that u modulus t u star equals the square root of this operator. And by the previous line, it is just the modulus of t star. Okay, and finally, if we now multiply the modulus of t star by u, we get the following. So by the previous equality, this is u modulus t, u star, and u. And now we apply formula 1 again. So this is just the modulus of t. And by formula 1, this is u multiplied by modulus t. But this is our operator t. And that's it. So we get the second formula, the second polar decomposition formula. T equals modulus of t star multiplied by u. So this completes the proof of our theorem. Okay. Now, in conclusion, let's prove the uniqueness of the polar decomposition. So one more theorem. The uniqueness of the polar decomposition. So we suppose that T is a bounded linear operator between two Hilbert spaces, H1 and H2. And let's consider its polar decompositions. When I say that these formulas are polar decompositions, I mean that U has all the properties mentioned in the previous theorem. That is, the kernel of U is the orthogonal complement of the image of the modulus of T, and the image of U is the closure of the image of T. Okay, and suppose now we have so part one. This is the uniqueness of the first polar decomposition. Suppose that T equals the following product, Vs, where V is a partial isometry from H1 to H2. Partial isometry from H1 to H2. S is a positive operator. Oops, what's going on? Oh my God. Okay, so we suppose that T can be decomposed in the following way, where V is a partial isometry, S is a positive operator on H1, positive operator on H1, and the kernel of V is the orthogonal complement of the image of S. So basically, we suppose that we have another polar decomposition of T, which is economical in the same way as the standard polar decomposition is economical. Then I claim that V equals U and S equals the modulus of T. So our original polar decomposition is unique. And we have a similar result for the right, for the second polar decomposition. So we suppose that T is the product as V, where V is partial isometry from H1 to H2. S is a positive operator on H2. And the image of V is the orthogonal complement of the kernel of S. And again, in this case, I claim that V equals U and S equals the modulus of T star. So the right polar decomposition of T is also essentially unique. Okay, so let's now prove this result. So first of all, let's look at part one. So we assume that T equals Vs. So this is our assumption. We take the joint operators and we see that T star equals SV star. Now S is positive, and so in particular it is self-adjoint. And so T star T equals S V star Vs. And now we use the same trick as in the proof of the previous theorem. Namely, we observe that V star V is the orthogonal projection onto the orthogonal complement of its kernel. Just because it is an orthogonal projection. And by lemma 1, this kernel is simply the kernel of V. Oops. The kernel of V, orthogonal. And by assumption, the kernel of V is the orthogonal complement of the image of S. So this implies that this is the closure of the image of S. This follows from the assumption of the theorem. And this implies that if we combine V star V with S, we get S. So this operator, V star V, is identical on the image of S. And so if we now go back to this formula, we conclude that t star t equals s squared. And by taking the square roots, we conclude that the modulus of t equals s. Okay, so s is the modulus of t. And now we want to show that v equals u. To show that v equals u, we do the following. We observe that t can be written in this way. Oops, this is just u, sorry. So we can write t in this way, and also in this way, because we already know that s equals the modulus of t. So this implies that u and v are the same on the image of the modulus of t. And hence they are the same on the closure of this image. But on the other hand, if we look at the orthogonal complement of this subspace, we see that both u and v vanish on this orthogonal complement, because the kernel of u equals the kernel of v equals the orthogonal complement of the image of s by assumption, image of the modulus of t. You know that s is the modulus of t. Orthogonal complement. Okay, so this observation together with the previous line implies that u and v are equal to each other. And this completes the proof of part 1. Now part 2 is a simple exercise for you. There are two ways, essentially. We can just repeat essentially the same argument, which is quite easy. But maybe it is even easier to apply part 1 to the joint operator. And by doing simple manipulations with the joint operators and orthogonal complements, we can show that 1 and 2 are essentially equivalent. So anyway, this completes the proof of the uniqueness of the polar decomposition. And this is the end of today's lecture. So at the next lecture, we first discuss a nice application of the polar decomposition, a nice topological application of the polar decomposition. Namely, we'll show that the unitary group of a Hilbert space is a strong deformation or retract of the general linear group of the space. And then we begin to discuss the spectral theorem for normal operators on Hilbert space. So we'll, as a first result, as a first form of the spectral theorem, we will show that each normal operator on the Hilbert space is unitarily equivalent to the multiplication operator acting on a suitable big L2 space, on some measure space. Okay, so that, thank you, that's all for today. And as usual, at